Hello, my name is Alexander Borzunov, and today I'll present Petals, a distributed system for inference and fine-tuning of open large language models, such as Bloom with 176 billion parameters. Petals allows you to run such models right from your desktop computer or Google Colab, using a swarm of GPUs hosting different parts of the model. These GPUs are provided by volunteers from all over the internet and pulled together into a decentralized system similar to BitTorrent. On the screen, you can see a status page listing many servers of different capacities hosting blocks of Bloom and BloomZ models. In fact, any user with a GPU can join the swarm and increase its throughput by running a Petals node on their computer. Next, clients can form a chain of consecutive servers to run forward and backward passes through the entire model. If some servers leave and create a gap or a bottleneck in the system throughput, other servers may change their positions to close this gap or eliminate a bottleneck in the system throughput. Now, let me show how to use the Petals client to run inference or fine-tuning. First, let's install the Petals package. The interface of the Petals client is compatible with the Hugging Face Transformers library. Running a distributed model is no more difficult than running a model hosted locally. You don't have to understand all the networking and load balancing algorithms Petals uses under the hood. Let's start with creating a distributed Bloom model. This machine will download a small part of the model weights, about 8 GB, and rely on other computers in the network to run the rest of the model. Now, let's try to generate something by calling model.generate method. This method runs gridded generation by default. However, you can choose other generation methods like top-P or top-K sampling, or even beam search by passing the corresponding parameters. For example, we can pass temperature and top-P parameters here. If you'd like to use the model in an interactive way, you can use the Inference session interface. This interface provides a simple way to print generated tokens on the fly or make a chatbot that responds to humans' phrases. The Inference session looks for a sequence of servers that will run successive inference steps and store past attention caches. This way, you don't need to rerun previous tokens through the transformer every time. If one of the remote servers fails, Petals will automatically find a replacement and regenerate a small part of the caches. This happens invisibly to the user. As you can see, the generation speed is more than 1 token per second. If you don't have enough GPUs to host the entire model yourself, this is much faster than what you get with other methods, such as offloading. Even though the internet is much slower and less reliable than your GPU bus, Petals, which communicates over the internet, is still 10 times faster, since it sends over the network only the neural network activations, that is, megabytes of data, instead of all the network weights, hundreds of gigabytes. We can extend the code above to accept users' inputs, making a simple chatbot working inside one inference session. So, for example, here we accept some inputs from a human and send them to a chatbot that generates the response. Then we can pass the next phrase to the chatbot. Note that you can package this code as a web application that uses Petals under the hood and is easily available to the outside users. Now, let's take a look at how all this works under the hood. So, the model you're running is the actual Bloom 176B, but only a part of it is loaded into your machine's GPU. Let's have a look under the hood of this PyTorch model. As you can see, word embeddings and some other layers are regular PyTorch modules hosted on your machine, but the rest of the model, for example transformer blocks, is encased in the remote sequential class. This is an advanced PyTorch module that runs on a distributed swarm of other machines. Still, you can access individual layers and their outputs, as well as run forward and backward passes through them. In general, you can mix and match distributed layers like in regular PyTorch, and even insert and train your own layers, for example adapters, between the pre-trained ones. Surprisingly, in Petals, each user can fine-tune the language model for their own task, simultaneously with other users. Let's see how to do that. While the remotely hosted transformer blocks are frozen, to keep the pre-trained model the same for all users, trainable prompts and parameter-efficient adapters are usually enough to make Bloom solve a variety of downstream tasks. You can run forward and backward passes through the pre-trained transformer blocks hosted by remote servers and optimize trainable parameters or soft prompts hosted locally. So, in case of trainable prompts, Petals supports prompt tuning and deep prompt tuning out of the box. You can see the scheme of the deep prompt tuning on the picture. To use this functionality, we should create a new model and specify tuning mode deep p-tune. Also, we need to specify some prefix length, that is the number of trainable soft tokens. We have created a model that by default continues the classic phrase "a quick brown fox" with the text jumped over a lazy dog. However, we may fine-tune a model on some trivial task. For example, we may force it to say that the fox actually did not jump over the lazy dog. So we can create this simple data set. For demonstration, it will contain just one example and fine-tune the model on it. You can see that the loss is decreasing, and actually after a few training steps the model will actually tell that the quick brown fox actually did not jump over the lazy dog. Let's skip the rest of the training and instead move to more advanced training techniques. That is, for example, adding trainable adapters between some transformer blocks of the pre-trained model. The layer weights and the corresponding optimizer statistics for these adapters will be stored locally. So first, we are creating the model that uses parts of the original transformer blocks, but inserts an adapter between them. We will use only the 10 first blocks for this demonstration. Now, we can train a classifier based on this updated model. In the classifier, we will just add some classification head like this in the end of the model, and then use the atom optimizer to train its parameters. As you can see, the loss is decreasing again, so the training actually happens. Finally, it's worth saying that Petals is a community-run system, so we rely on people giving out their GPUs to increase the swarm's capacity. Actually, connecting your GPU to the swarm is as easy as running these commands in Docker or an Anaconda environment. Petals is 100% open source. You can find the source code and documentation in our GitHub repository. Please note that when you use Petals, your data is processed by other people in the swarm. They don't see your data directly, but may recover parts of it from the activations and hidden states of the language models. If you work with sensitive data, you can set up your own independent swarm among people or organizations you trust. We provide instructions for that in our repository. Finally, we provide instructions for adding new language models to Petals, as well as answers to frequently asked questions. Thanks for listening, and see you at the conference.